Hi. Right now we're going to discuss the mechanical energy transformation lab that you already completed. I'm going to review some of the things that you may have seen or that you should have seen, and then I'm going to transform our data into equations that we can actually use to predict velocities, predict height, how high something will go, uh, and and do overall math using energy. This is probably the greatest concept that we can have in this chapter, and so you need to pay really close attention on how to use this equation later on whenever I work an example problem. Uh, but right now, let's just go ahead and get that equation. The major concept that we should remember from the previous chapter is that the type of energy that, or not the previous chapter, but the previous section, is the type of energy that we are talking about is called mechanical energy. So I'm going to represent that with ME, which stands for mechanical energy, and that is just kinetic energy and potential energy. And so I need to know the concept that the total mechanical energy of an object includes both its kinetic energy plus its potential energy. And using that relationship, I should be able to come up with some ideas of what the equation should look like. Now, I've already conducted this experiment, and so I'm going to go ahead and pull up my data so that we can see, or so that I can see it, and then I'll just go ahead and tell you what I've got, or what I came up with. I went ahead and drew this picture, and so you can see this is how my experiment went. I measured the potential and kinetic energy at this location, and then I also measured the height and velocity so I could calculate the kinetic and potential energy at this position, and then at position 3 also. So I started at position 1, went to 2, and then 3. And I'm just using this to confirm this change in if there is definitely a change or a pattern in the change of energy. At position 1, I had a kinetic energy of 0 because I did not release my cart yet. So the kinetic energy itself was 0. Because it's not moving, it has no motion, so its kinetic energy is 0. The other one is the potential energy at this location. I measured the height and then I calculated, and I'm not going to show you how I did that calculation because we've already seen it. But I came up with 123 joules. Now at position 2, I measured my velocity and then I calculated my kinetic energy, and it was 50 joules. And then I also measured my height and calculated my potential energy, and that was 73 joules. And then at position 3, my kinetic energy was 100 joules, and my potential energy at this location was 23 joules. Okay, now the pattern here is quite nice. It's quite easy to see, especially if I think back at the concept where my mechanical energy is the sum of both of my kinetic and potential energy. So in this case, if I add them together, I get 123 joules. In this case, I get 123 joules. And in this case, 123 joules. Hopefully you saw this in your lab, because this is what the whole point of this was to show that our mechanical energy does not change over time. And so if I look at some math involved or the concepts involved, well, I know that the mechanical energy at location 1 equals my mechanical energy at location 2, and that also equals my mechanical energy at location 3. So I want to put this in terms of initial and final, so that we can compare the energy of an object at a starting point to the energy of the object at an ending point. And so in this case, that we'll call that my initial mechanical energy, and we'll call this one my final kinetic energy. Okay, because that's the change, or the energy transformations from location 1 to location 2, where I start at 1 and then I end at 2. And so having this, I see that my mechanical energy is just kinetic energy plus my potential energy. Now, I want to go ahead and highlight this, because this is the concept that we should be getting from this whole lab. Is the fact that our initial mechanical energy has to equal our final mechanical energy. So let's go ahead and flesh this out. My kinetic energy initial plus my potential energy initial has to equal my kinetic energy final plus my potential energy final. Okay, and this is in the absence of friction, and we'll talk about that stuff later on in the chapter. But this is an additional concept where I'm moving this mechanical energy into its components. And then likewise, I can actually move these even further into their components, where I have my initial kinetic energy is going to be 1/2. Well, my mass doesn't change. Instead, it's just the velocity is changing. So my initial velocity squared plus my mass and the acceleration of gravity doesn't change, but my height changes. So that's going to be my initial height equals 1/2 my mass times my final velocity squared plus my mass times the acceleration of gravity times my final height. Okay, so there's my equation in this situation. Now we've talked about an additional form of potential energy, and in this instance all we have is gravitational. But if I was to put a spring or anything that deforms like a bouncing ball, well, it's going to have not gravitational, but elastic potential energy. And so I need to add that term to this equation right here. And so this long equation actually becomes a little bit longer. But it's somewhat nice because if you don't have a spring, you don't have to worry about the spring parts. Just like if the object is not falling down, you don't have to worry about gravitational potential energy. And if the object is not moving, then you don't have to worry about the velocity or the kinetic energy. So let's go ahead and write this out as 1/2 my mass times my initial velocity squared plus my mass times the acceleration of gravity times my initial height plus 1/2 my spring constant times my compression or stretch squared. And that's my initial compression or stretch. If I don't have a spring, well, that's 0, so that term goes away. And then that's going to equal, on the other side of the equation, I'm just going to finalize all of these. So down here I'll write it 1/2 my mass times my final velocity squared plus my mass times the acceleration of gravity times my final height plus 1/2 my spring constant times my final compression squared. All right, and that finishes off the equation that we are going to be using for this section. And it's a long equation. I'm going to show you how to use it, but it's really not that difficult to use. So don't get frustrated at how long it is and how many terms there are. A lot of these will cancel out, such as, and we can look at this real quick. If I look at my initial kinetic energy here, excuse me, well then my initial kinetic energy is 0, which means my velocity is 0, and so that actually goes away. It's not there anymore. And then I don't have a spring, so that's gone, and so is this spring right here. So I'm left only with 3 of these terms. So we will actually learn how to cancel these out and to get rid of some of the terms that are not available or not helpful for our situation. Okay, and then I'll see you on the example problems.